Hello, good afternoon, everybody, and thank you for joining today's webinar. We're going to get started now. We have about 30 or so people in attendance. That's great numbers. I'm sure we'll see a few more join shortly. My name is Michael Dutton, and I'm very excited to announce the continuation of our educational series for all TAC members. We aim to strive to teach the basics of tunneling themes that aren't always taught in school, but are certainly beneficial to everybody in industry, despite your background. If you're a student or just starting your career or someone that likes to continue to learn, you're definitely going to pick up something new in each of these presentations. We're running today a live event, so if you have any questions, please type it into the Q&A box, and we'll get those approved and get them addressed at the end of today's presentations. You're also certainly welcome to give each other a thumbs up for those questions that are more popular. We can try and address them first as well. So I'm delighted to announce today's speakers. We have two. First is Jonathan Apatin. Jonathan holds a mining engineering degree from McGill University in Montreal, Canada. From 2012 to 2021, he has held various roles in mining companies, Windsor Salt and the US parent company, Morton Salt, working as a mine engineer, production engineer, and then a general supervisor. Jonathan completed his PhD in geological engineering in 2020, while working at Weeks Island mine in southern Louisiana. In 2021, Jonathan transitioned to an academic role as an assistant professor at ETS in Montreal. His research work focuses on blastability, rock mass characterization, and time dependency in rock engineering. Jonathan is joined by Marc-Antoine Rose. Marc-Antoine is a drill and blast consultant with BBA Consultants. Mark graduated as a mine engineer at McGill University, and he has held various engineering roles with explosive manufacturing companies, Dyno Nobel and Maxim. Mark transitioned into his current role with BBA in 2018. He now supports mining operations and construction projects with the design and optimization of blasting practices. His role with BBA, Mark gets to offer training and educational support with private companies and academic institutions. Mark has given several lectures at McGill University and ETS to share his passions to date. Now over to Mark. Thank you. Or to Jonathan, sorry.
Excellent. Thank you, Michael. Can you confirm you hear me all right?
Loud and clear. Thank you.
Excellent. Well, thank you, everybody, for joining. My name is Jonathan Aubertin. I'm a professor at École de Technologie Supérieure, ETS, in Montreal in the Construction Engineering Department. This presentation today doesn't aim to be extremely in-depth or technical. It's really to get a sense of what rock blasting is all about, especially when we consider tunnel construction. So the presentation is divided in two parts with the two presenters that were already introduced. My part will be a bit more generic rock blasting 101, trying to give you a sense of what rock blasting is all about and some useful terminology to understand the mechanisms behind blasting. The second part will be more practical in the sense of talking about case studies, tunnel constructions, and how explosives are used in the civil engineering industry as a whole. The content will go as follows. First part, rock blasting rationale. How rock fractures and breaks when you're talking about explosives application, basic terminology. Some general content, part two, cell explosives, and the case study around the McGill University that Mark will give. So the very first thing is about rock blasting is intro is like, why are we using rock blasting and for what purpose? So I think from a general sense, everybody knows about blasting, everybody knows about explosives, everybody understands that rock is often broken down, loosened, fractured using explosives, but the actual engineering concept behind them are not so common. But there's various applications, from very fine and detailed, precise applications for some specific construction projects to just some massive bulk blasting operations in mining industry. So blasting is very core to the mining industry. It's something that we see a lot in the mining industry, whether it's underground or surface. It's something that we see all around. It's almost essential to a large sense to everything that's mining related. Then obviously it's something that you see a lot in the construction of underground excavations, including, for example, tunneling operation. It's very central to these applications. Something that you see a lot is something that is still very prevalent despite the growing popularity of conventional miners and tunnel boring machines. Blasting, for those of interest, is also very common in some highway and railroad construction. You see a lot when you go to mountainous regions where you have nice and smooth roads. You'll see those nicely blasted surfaces along the road with those half moon, clearly demarked position of the blasted surfaces like you see on this picture today. You'll see that very commonly. And obviously tunnel, like I mentioned. So a few notions. Rock blasting has been around since a long time, since the invention of the black powder in the 17th century. Blasting took a major turn with the invention of the dynamite by Alfred Nobel in 1867. Rock blasting to this day represents the most efficient and cost-effective means to break rock. It's important to understand this rationale of cost effectiveness. It's the most efficient, cheapest, the easiest way to break the rock, given the mechanism behind of trying to fracture the rock in tension rather than trying to compress it. There are other means of doing this, whether it's continuous miners, tunnel boring machines. By cost-wise and energy consumption-wise, this remains by far the most efficient way of doing this. Hence, its prevalence in various applications, especially in the mining industry. If you talk about to a blaster tomorrow, you'll see that there's a fine line between the technical science, the technical rationale that this operator, this blaster, knows, and what he would refer to his experience, but also most you hear about it as art. And I think it's important to demystify the technical from the art, or actually understanding that the art of blasting essentially relies on key engineering precepts, which I'll try to showcase briefly. So how does it work? So how does rock blasting take place? How does this happen? What are the key mechanisms behind it? So the first, I guess the chemical bit of blasting relates to the detonation reaction. The detonation reaction relates to solid or liquid, the explosive component of the blast hole, that transform into a gas. This chemical reaction, this transformation takes place at supersonic velocity. It happens faster than the speed of sound in air or in the material that you're considering. This velocity, this component is important to take into account because at subsonic velocity, you're essentially talking about combustion. You can still have pressures, heat, and a change from solid to gas, but what the marks that as being a detonation, which is the chemical reaction we rely on in blasting, is the speed at which the detonation reaction takes place, which is supersonic. So when you have this material, this explosive turning into a gas, you exert great pressures on the rock surface in that blast hole. That pressure is sometimes thousands of GPAs. These are massive amounts. Now, you don't necessarily have thousands of GPAs being induced or exerted all to the rock mass being broken. It's essentially to the blast hole, but this pressure allows to damage, break, pulverize rock, and then initiate fractures a way that will eventually propagate to a nearby free surface. Here's a bit of a visual representation of what the detonation takes place. So you have, if you think about the initiation process, you have a cartridge of explosives here. The initiation took place on the left hand side, and as the detonation takes place, it propagates through the explosive product from left to right at the detonation velocity. Now you have this gas expansion, and then you have the undetonated component on the right. This transition point from detonated to not detonated, growing gas to still virgin, is called the Chapman-Jouguet reaction. Without going into much details of the chemical aspect of this, it's important to visualize how this propagates, because if you have a big 10-20 meter long blast hole and you have the detonation taking at the place at the bottom of the hole, where you have the same propagating detonation reaction going from bottom to top and exerting pressure to the blast hole at that sequence. So what happens if you look at this in 2D during the blasting event? You have this several thousands of GPAs being applied to the rock mass, very high pressure. The rock right near to the blast hole is pulverized, crushed, completely damaged. This damage zone is not very large. We're talking usually 3 to 6, 7 times the diameter of the blast hole. But that rock is completely crushed, completely pulverized. Then if I skip the second part, I'll go right to the third part. You have radial fractures that emanate from this completely crushed part. In between number 2, you have a mix of radial fractures and completely pulverized. It's essentially a transitional damage zone. But what's important to realize is very close to the blast hole, you have pulverized rock, damaged rock. And beyond this, you have a series of radial fractures that emanate radially away from the blast hole. It's important to also acknowledge that the crushing piece, this pulverizing of the rock, is where a lot of the energy of the explosion is lost. Hence, you don't actually have thousands of GPAs being transferred to the rock elastically. You have a lot of that energy being lost due to energy losses due to the crushing and pulverizing of the rock. What's very important from the cratering, the fracturing process, is the later stage, the radial fracture propagation, which we'll come back to in a second. So now you have those 3 zones: the pulverized, the damage, and the radial cracks. Beyond the cracks, beyond those fractures, you have this pressure that was reduced, dampened by the damage, that is now transferred elastically to the rock. In other words, you're sending shock waves away. That's where, whether you're talking about seismic activities, earthquakes, or blasting, that's what you feel. That's the shaking that takes place. This energy is transferred to the rock. Past damage no longer damaging, at least not right now, and sending waves that is vibrating everything and potentially impacting things around constructions. So this is a bit what it looks like. I think what's important to visualize is on the right how the wave propagates. It's emitted away from the blast hole. The primary, whereas when you're thinking earthquakes, you're always considering the Rayleigh waves, the surface wave, the shear waves, and blasting. What really is important to us is that primary, that compressive wave, what we call P wave, that compressive pressure emanating from the blast hole towards wherever you're going. That's the most important wave. That's the highest amplitude in terms of stress wave being emanated by the blast hole. This is what we are designing the blasting based on. So how does it look? Before we talk about creating the actual crater from those waves, it's important to visualize a bit what this should look like and what we're talking about. So this is a geometry we refer to very often in rock blasting. This is a bench geometry, but you could easily turn it sideways horizontally and look at a blasting configuration in the tunnel. And we'll get to this in a few minutes, but I think this geometry is very important. You have, if you consider a single blast hole, a single hole being loaded with explosives, that hole is going to be parallel to some kind of a free surface. You need that free surface for blasting. We'll get back to that in a minute as to why you need this. But basically, that hole is a certain height or length, depending if you're horizontal or vertical, and it's a distance B, what we call burden, away from the nearest free surface. Then from there, you have the cratering taking place. So you have the burden, which is typically the most important dimension for everything practically related to blasting. That it defines the geometry and the shape of the crater. You have the height, like I mentioned, which could also be the length of the blast hole if you're considering horizontal blasting. And then you have the resulting crater, which you can measure in different ways, whether it's the width of the crater or the breakout angle or the cross-sectional areas. Many different ways of looking at this, but this is the generic configuration of a blast and what it looks like. Now, when you're talking about underground blasting applications, you have a very similar geometry, except from the get-go, you're mining horizontal, you have a face, you don't have a free surface. If you come back to this, you have this blast hole, this benching configuration, which is very classic in mining. You have a big free surface you're using for your blasting process. In underground mining, especially in tunnel application, you don't have this free surface. You have to generate this. This is what you see in the center of this very simplistic, very conceptual blasting design. You have the cut in the center of the face. The cut is the very first set of blast holes you're going to blast, very closely set apart, essentially very damaging and pulverizing and changing the density of the centerpiece so that you essentially generate a relief void. reflective surface at the center that will act like that free surface and the bench that we were talking earlier. Then you have, depending on the dimension, the size, and the geometry of your tunnels, a series of blast holes that are very classic. Stoping holes are usually what's coming down inside once everything is open in the center. Then you have on the floor lifters. Those lifters is usually what you try to position closely spaced and with a certain timing to try to give yourself a nicer, smoother floor. Then you have also contour holes at the roof and the walls. Again, that you're going to specially space a bit closer and change the charge and change the delay a little bit to give you a nicer and smoother wall and surface. So now that we have a sense of the geometry, now that we have a sense of what it looks like, the question becomes, we know we've got the P wave emanating, but what's actually breaking things? It's important to realize that the crushing, the pulverizing that I mentioned earlier takes place, but it's not what's driving the overall rock blasting process. When you're blasting, whether it's in tunnel or in a mining environment, you're not trying to pulverize anything. That's not the point. You're trying to fragment the rock so that it projects and gets away, and you can conveniently move it around. So what takes place, this fundamental cratering behavior, which is very essential to understanding what rock blasting takes place, is you have those P waves, those compressive waves emanating away from the blast hole. Here's a very conceptual perspective. You have a free surface. Here is that blue line where the red lines are emanating from. That free surface can be the cut or the bench face. It can be different layouts depending, but that free surface reflect the pressure waves, the compressive waves in tension. Those tension waves, they travel back towards the blast hole. Now we remember, close to the blast hole, you have this crush zone, but you also have a series of radial fractures that emanated away from the blast hole. Those tensile waves interact with those radial fractures to essentially prop them open. Now, by propping them open, they expand them until they reach the opening, and that essentially yield a crater, prismatic in look and shape, that is driven by the expansion of those radial fractures. So while pulverizing and crushing does take place, what's important is that reflected pressure wave coming back in tension, propping open those fractures all the way towards the free face. Like I mentioned, this is again a conceptual look of a blast, but what I like to emphasize here is that we often refer to those craters as prism. The reason being simple is that the mechanism behind this is driven by radial fracture propagation and opening. So we just talked about this. We talked about fracture propagation. This is essentially driven and induced by shockwave, pressure shockwave coming back and being reflected in tension and opening further the fractures. But what about the gases? Well, the gases also have an importance. The solid liquid, the explosives went from a solid liquid to a gas, which have pressures. The gases themselves also have pressures, which are not necessarily inducing shock waves. They're still there as a pressure. They can open up the cracks, and they can also heave the muck pile. Their importance really resides on heaving that muck pile. There was a lot of tests being done in the 70s and 80s to showcasing this. They actually added metal plates at the end of a bench, a small scale model, to showcase that without the gases, if you put a vent tube in a hole without the gases, you'll still get shockwave fracturing. The block will still shatter. Without the shock waves only relying on gas, you barely get any fractures. So it's very important to realize that the gases have some importance in the heave, but the bulk of the blasting, the fragmentation, takes place from shockwave fracturing. 70 to 80% of the fragmentation comes from the pressure waves. There was a lot of testing done to showcase this, and it's important to acknowledge. So my final note that are relating to rock blasting engineering. So a bit of the things that when you're a rock blasting engineer, especially in tunnels, you have to deal with. Well, what you're trying to do, what you're trying to accomplish when you design a blast as a tunnel engineer, especially in blasting application, is to have a cost-effective pattern. You don't want to overuse explosives. This can be very expensive. That can be time-consuming. You're trying to generate a cost-effective pattern. You're also trying to control fragmentation. If you have blocks that are bigger than your shovel, you're going to have a problem. If you only have fines, if you only have small material, you're going to have muddy environments. You're going to have challenges handling that material. You're trying to get that fine, that ideal fragmentation. Then you're trying to manage vibration. And then I'll let Mark talk a lot more about vibration. I think he's got very interesting case studies to talk about. But vibrations are a big component of explosive engineering because you don't want to induce too much vibration, especially if you're constructing a tunnel downtown in an urban area where you've got buildings all around. Then of great importance is also gases. Everything that pertains to toxic gases, NO2, NOx, CO, CO2. These are gases that are the results of the explosive processes. Again, if you're not ventilating properly, can be a problem. But if you're using too much explosives, you're going all overboard, putting too much explosive, you can end up having too much gases. And it's the role of the engineers to control this, mitigate this, and measure this to make sure the workers are not overly exposed to those toxic gases. So this concludes my rock blasting 101 section. I'm happy with the timing I've got here. I'll stop sharing my screen just for a second so that my colleague can start sharing his, and I'll let him do his thing. You're up, Mark.
Yeah, setting it up. So you see this?
Yes, we can.
Okay, thank you. So there we go. Thank you very much, John. So to be able to access to reach that breakage mechanism, here are the few steps we need to do. And we're going to go through the different type of civil explosive we see in this industry nowadays. And we're going to finish with some quick slides about a project we worked on, BBA worked on downtown Montreal, which is a project that was that required to blast access shafts and tunnels with explosives. So step number one, when you have a hole drilled, you need to load it. So the very first step will be to install a detonator with a booster. So step number two will be then to load the rest of the hole with bulk or package explosive. So any type of blasting you do, there's always going to be a chain reaction. So you need a detonator, you need a booster, which is the green little cylinder, and then you need a column of charge. So your detonator will always be the first initiation that will initiate the booster, and then the booster will initiate the rest, or like the bulk part or bulk explosive inside the hole, either if it's package explosive or bulk explosive. There I put a note, I said, like, if the hole is greater or equal to 7.5 meter, you're going to have a second booster. If the hole is short enough, you only need one booster and one detonator. But if it's longer than 7.5 meter, as a good practice in the industry, you're likely to have a second one. And then step number three, we say we stem the hole. So basically, when you have a hole, no matter the length of that hole, no matter if it's vertical or horizontal, if you're open pit, quarry, civil, underground, whatever, as a good practice, you never load or you never bring the explosive all the way to the collar of the hole. You always leave a section that's going to be filled with inert material or crushed stone. So when your charge detonates, there's a certain confinement. As Jonathan explained, you have gases, you have a shock wave generated during the initiation. So basically having the upper portion of the hole stemmed with crushed stone, that's gonna keep most of the energy and the gas inside the rock, which is what we want to break. Then let's start with what we need to have an explosion, a detonation. So basically we need the detonator. In the industry nowadays, we have four types of detonators. We have the electric, the non-electric, that's also called non-L. We have the electronic and wireless detonator. Wireless, we're not going to cover it today. Basically, electronic and wireless, they're both electronic. Main difference, it's that one doesn't have a wire and the other one has one. Electric detonator, you might not see these type of detonators a lot in the industry in your career, because that's a type of detonator that it's kind of disappearing, because everyone's going towards electronic and still using non-L. One key thing you need to keep in mind, each of these type of detonators have their own initiation system. You can't initiate electronic detonator with a system used for non-L, and the other way around as well. If we look at the structure of each type of these detonators, so basically they're very, very similar with few differences. If you look at the right side of these detonators, well, when we say detonators, by the way, to me, a detonator is the aluminum shell. The aluminum shell, this is where you have your explosive. And if like these are cross section of these aluminum shells in which you have your delay and the primary and base charge. So as you can see on the right side of these illustrations, the primary and base charge are pretty much always the same, no matter the detonator type. But the key difference here will be the delay inside that aluminum shell. In the electric and non-electric detonator, they both have pyrotechnic delays, which is going to be can you see my, I'm going to turn on the pointer here. Yeah, so this section here for non-electric and electric, they're pyrotechnic delays. So these type of detonators already have pre-established delays, while the electronic here, that's a microchip. So these are not, you need to program electronic detonators with the delay you want to give each hole. Another difference between, let's say, non-L and electronic, let's look at these two detonators because they're the ones that are more likely to see in your career in the industry. The main difference here between electronic and non-electric is the type of tube or wire. So electronic is literally a lead wire, while non-electric, it's a shock tube that is filled with or coated inside with an explosive powder that we're going to cover in a few slides. So non-L type of detonator that it's used quite often in the civil and tunneling industry. So basically, one of the key components of a non-L, it's the tube, the shock tube. It's not a wire, it's a tube with 3 layers with an inside coating of HMX and aluminum powder. So basically, when you pinch that tube and you're able to fire the powder inside, this is how the current or like the fire is going to be given to the upper to both ends of that whole system. So basically, it travels inside when that powder inside fires. It fires at 2100 meters per second, which is a quite low velocity of detonation, as you'll see throughout my section of that presentation. One key thing as well is when that powder inside the tube fires, the tube will stay intact, even during the detonation of that powder and after the detonation. So if you get, like after a blast, you go back to the field and you still see those shock tubes, don't be scared, it's still fired. It's not because you still see the tube that these detonators didn't fire properly. There are a multitude of downhole and surface delays in the non-L world. Unfortunately, we can cover all these type of non-L detonator today, but keep that in mind. There are different applications. So as you can see here, we have 4 different types. There are some with surface connectors, different colors. One key thing is they all have the shock tubes. They all have at least one aluminum shell, which is the main part of the detonator, and they all have pre-established delays inside either the clip here that stays on the surface or the detonator, the aluminum shell that goes inside the hole. Same illustration that Jonathan showed earlier. So basically, when that shock tubes get pinched and the powder inside starts being initiated, it travels through, it burns and detonates. Well, I'd say more it's a detonation because it's 2100 meters per second, which is, depending on the tube, VOD here between 1800 and 2100 meters per second to be specific. So this is how the powder inside the tube fires. And here's a cross section. So we can see the different layers of plastic shaping the tube with the coating inside of HMX and an aluminum powder that is meant to give the initiation or like the current inside the tube to reach the aluminum shell. This is a video of a non-L loaded blast. This is to show you that there's a lot of energy generated when that aluminum and HMX and aluminum powder that fires inside the tube, and you can see it. So that's a blast where all the holes were loaded with had non-L detonators, and all the holes are connected or physically connected to each other. And you'll see this is quite impressive to see that even if the tubes don't get destroyed, you can still see a lot of energy. It's like you can see the light over the blast surface. So one key thing you need to keep in mind when you're using Nonel is that connection need to be physical. You need to connect the hole in the order you want the fire to be given between each hole. So your first row needs to be connected, like the holes in the first row needs to be connected together first, and then you connect it to the second row and third row and fourth row. While when you're using electronic detonators, you don't need to follow a specific connection pattern. So that's the main difference. As I said, electronic detonators, they're 100% user programmable detonators. You can give them increments of 1 millisecond at a time. Most of the time, I'd say it depends on the explosive suppliers, but like the window in which you need to program your detonators will be between 1 millisecond up to sometimes 30,000 milliseconds to 30 seconds. So for underground blast, 30 seconds, well, let's say for tunneling, 30 seconds, it's quite long, but when you start being in open pit mines, big mining operations, sometimes 30 seconds when you have a lot of individual blasts, all on the same network, 30 seconds sometimes can be quite handy. These type of detonators are two-way communication type of detonators. It means that when it's programmed, you can communicate back and forth with it. So you program it, and when it's time, like when it's all installed, your blast is loaded, and it's time to fire. Before you're allowed to fire your blast, your system will make sure that each detonator responds, and each detonator is ready and will fire. While when you use the Nonel type of detonator, you don't have an insurance. If you only have one detonator, Nonel detonator per hole, when you press on that button, on that red button, you don't have you don't have an insurance that everything went off. That's a reason why you always need to have at least two. To me, as a good industry practice, you should always have 2 detonators per hole, Nonel detonator. It's unlikely, they're unlikely to fail. Usually the explosive supplier will say it's 1 over a million, so it's unlikely. But when you are using electronic detonator, before you fire the shot, you're 100% sure that everything responds. Another key aspect of the electronic detonators, even though that's a detonator that, of course, it's more expensive than the Nonel type of detonators, but you have more controls, you have more flexibility. You can play a lot more with your vibration, because each hole, each charge firing will generate a shock wave. And then if you use specific design software and you want to play with millisecond increments, you need the electronic detonators. So in this case, when you're in extremely sensitive areas, you need to use these detonators, because when you're using Nonel, as I told you, they already have pre-established delays. But these pre-established delays, they're pyrotechnic delays. So they have errors. They're like these delays, they're just burning. While the electronic delays, they're microchip, they're 100% accurate. So when it's time to do vibration control, fragmentation optimization, or dilution control, electronic detonators are the best one to use, definitely. Then there's going to be the booster. So as I told you, flue size ago, there's always going to be one detonator combined with a booster, and then the booster will give the initiation to the column of charge. So this is the second step in a hole loaded with explosive. So basically, booster are used because the third part of your chain reaction, which is the bulk explosive is not sensitive enough to only be initiated with the detonator. You always need that second step, which is the booster. So basically, boosters are another term used in the industry, cast boosters. So basically, we're going to just pour a liquid mix of PTN with sometimes other high explosive, molecular explosive. The main one we see in the industry is pentolite. So it's a mix of PTN and TNT. So on the 2 illustration or pictures on the right side of the slide, these red pellets, these are going to be 100% PTN, and these will be specifically placed in the cast, and the rest of the cast will be the mix of pentolite. While this slide here, this little section will be pure PTN, because this is where your detonator will go. So this is where the section of your booster needs to be the most sensitive. VOD here, so remember this term, velocity of detonation, extremely important. We see here PTN 7,550 meters per second, which is extremely high. So you need, when you initiate a column of charge, you always need to initiate an explosive with another explosive that initiates faster. You always need more energy, more pressure from the giver, from the donor to the receiver. So that's why PTN is used for boosters, to be 100% sure that no matter the bulk explosive you're using to load the black holes, that they're going to be initiated with something that has a higher pressure. So 7,000, over 7,000 meter per second is usually an explosive. It's one of the fastest explosive in the explosive industry. So there are various models. Some are casted with plastic molds. Some are with cardboard. It doesn't really matter, but like they have they're a very specific usage. But the main ones will always be built this way. So this is how you're going to install detonator inside the booster. So no matter what's the explosive supplier and the model of your booster, they're always going to be one side with one hole and the other side with two holes. So basically you insert the detonator on the side that only has one hole, and then on the other side you loop it back in the cap well, and in the cap well that detonator needs to go in that specific well, because this is where you're going to have the red pellet, the pure PTN section, which is the most sensitive section of your booster. Then now the third part of that chain reaction inside the blast hole, which is the bulk explosive. So there are a few different types of bulk explosive. Since we only have 1 hour in this presentation, I went directly to the bulk explosive, which is called emulsion. There are going to be other types, but I'd say nowadays this is the bulk explosive that has the best water resistance, and this is the explosive the mostly used nowadays. No matter if you're in quarry, civil construction, underground, tunneling, mines, bulk emulsion will be and package emulsion, because you can have it in two different forms, so either in bulk or in cartridges. So this is the bulk explosive, the mostly used. It's a water and oil structure, so basically it's a mix of few components, but mainly it's ammonium nitrate, because ammonium nitrate has the oxygen, and it's mixed with a fuel phase and some other components, a little bit of water as well. The main advantage of bulk emulsion is that you can play with its viscosity and its density. So no matter, like, depending on your rock mass parameters, depending on what type of blast you want to do, if you want to reduce your gases, have more shock, more heat, you can play with your density. You can play with a component inside. On those two pictures, you see there's one that is pure emulsion at the top right, and while the bottom left picture, you can see there's small white spheres, which is solid ammonium nitrate, which is another type of bulk emulsion mixed with ammonium nitrate krill, and it's meant for some other applications. Again, you can see here, I put again the VOD, because to me the VOD and blasting engineering, VOD, velocity of detonation, is extremely important. So depending on what type of bulk emulsion kind of component you put in your emulsion, you can see there that the range of VOD can be extremely large, but you can bring an emulsion up to 6,500 meters per second, which is quite fast for bulk emulsion. Then package emulsion, so that's the exact same thing I just showed you, but put inside cartridges. So this is in tunneling, blasting. This is one the mostly used type of explosive. So this is emulsion, but it's put inside cartridges or plastic films. So basically, the main advantage is that it's easier to load. It's easier to carry. You just need to carry boxes. You don't need to bring the big bulk truck, because underground sometimes for tunnels or shafts, bringing bins and trucks, it's a bit more complicated. So bringing boxes with package emulsion is easier, and you can control more easily the amount of kgs of explosive you put inside the hole, especially when you need to respect your vibration. You don't want to start losing explosive and creating bombs in cavities if they exist. So having package emulsion gives you a better kgs or explosive amount control. So these explosive, again, they can be used depending, there are different mixes, as you can see, the different, like some have different colors, some have like some other components. You can still see the solid ammonium nitrate prill inside some of these type of product. They have different form, different diameters, different lengths. So they have a lot of different applications, from pre-splitting, decking, if you have difficult hole conditions, if you're doing trenching where you only have one free face and where all the holes are extremely close to each other, where you can sometimes have extremely high shock wave levels. Another type of packaged explosive will be the dynamite. Dynamite is still a product we see in the industry, but it's kind of disappearing because dynamite contains nitroglycerins at 50%. Nitroglycerin is extremely sensitive, extremely powerful, but extremely sensitive as well. And there's been, over the years since the 80s, there's been a lot of, and even before that, there's been a lot of accidents at manufacturing plants. Literally, when the plants totally disappear when you start having an accident in the plant and it starts, the plant starts burning and exploding. It's just there's nothing to do. Like it's too late. So they realized that the company started going more towards the package emulsion. Even though dynamite is extremely powerful, you can see its range always between 5,000 to 6,000 meters per second. You're still going to see it in the industry once in a while in very hard ground conditions. That's a product that can withstand high shock in presence of water. For example, when you have a lot of holes near close to each other, the dynamite can withstand the shock from neighbor holes firing before. And I still wanted to do it because in tunneling, once in a while, you're going to see the dynamite. And the last type of civil explosive you're going to see in tunneling will be the detonating cord. So basically, detonating cord, it looks like a rope with a core of PTN. PTN, it's the exact same explosive we're going to find in the boosters. That's the exact same thing, and that's why we have a very similar VOD. So now we're going to go, we're going to talk about that case study. I kept it very, very brief. That's a project we worked on that was downtown Montreal. Under the McGill Hospital. So there was an already existing tunnel network. So we needed the already existing network was on the picture is the blue and green sections. What we needed to blast was the red section. So we had one access shaft and 3 accessory shafts or auxiliary shafts. And then the network of tunnels linking these shafts together. It was done between April 2014 and April 2015, and as I said, it was right under the McGill Hospital. So as you can see, we were extremely close to already existing structures, building hospitals, surgery rooms. So vibration control was had to be followed. So the amount of kgs or explosive that were put in each hole was needed to be followed. There were seismograph everywhere. Unfortunately, only that case study could have been presented for over 2 hours. So I just wanted to show you the specific blast designs we use for the main shaft and the tunnel sections. So basically, the contractor came to us, and the engineering company in charge, or it was actually Nelson at that time, who was in charge of all the excavation. And they came to us. Hatch was also involved, of course, because there's in Montreal or anywhere in Canada, as soon as there's we're talking about tunnel, Hatch is involved. So they came to us because they realized they couldn't do it with TBMs or with specific tunneling machines. They knew they needed to do it with blasting because the excavation were quite small. So at first we look at the excavation, like the amount of rock we needed to excavate for the access shaft. So we just went with, again, the first, in terms of design, you need to look at your vibration. So there's some, unfortunately I didn't include them in my presentation because it would have taken too long, but you need to start with to know what are your limits, your vibration limits. You need to respect to the surrounding structures nearby your excavation site. So basically here, because of those vibration limits we needed to respect, for the access shaft, we cut down, or we split the excavation in benches of 1.5 meter high, and each bench was separated in 3 blasts, as you can see on the left picture. So basically, each bench was separated with the sinking cut, which was the first blast of each bench, and then once you have your free face created here, you can blast your second section of that bench, and then we finish with a slightly bigger blast, which is the third part of each bench. As you can see here on the perimeter holes, before you even start sinking down your shaft, you need to drill these perimeter holes. I think, yes, and we see it very well in that picture. So, because as you start going down, you need, like, that's the best method in the civil industry, used to have a well or sheared wall. So you're gonna have you're gonna drill closely spaced holes along the excavation limit. These reports you see here, these were borehole deviation reports generated from borehole probes that you put in the hole, because you want precision is key when you're drilling and you're blasting these kind of excavations. And you see there, the guys are just started drilling a new bench. Yeah. So for each, I wanted to show you these, like the loading procedure, loading specifications, because we just went over the different type of explosive used in the industry. But now I wanted to show you that case study just to show you that we were talking about package explosive, package emulsion, and this is exactly what they used there for this specific project. So they used package emulsion, they used detonating cord, and they used no-nail type of detonators. So basically, if we look at the perimeter holes were the holes here in green all around the excavation limit, where the holes are closer in spacing. So basically, they only put one, when they were blasting these holes, they were only putting a half a stick of package emulsion at the bottom of the hole, connected one string of that cord. So that string of that cord, here, you don't need to blast the hole, you don't need to load entirely the hole. You just want to create a shear wall. So you don't need that much of explosive in these perimeter holes. Just one string of that cord, 400 grain, is enough to just create that split, to have the holes, because they're closely spaced, they're just going to connect and create that shear wall. And this is how you get those half moon or half barrel all along your perimeter or your excavation limit. So this is how you do pre-shear or pre-splitting. This is where the term comes from. And then for the mass holes inside your excavation or inside the bench, the guys were using 2 sticks, or from 2 to 2.5 sticks of package emulsion. So this is on the excavation while the shaft was going down. So you see the guys there, they're in a new bench. So this is blast number 1. And here there will be blast number 2, and then blast number 3 would be right here. And as they go down, they protect the wall as well. But you can see half barrels. These half barrels are obtained from not loading the holes entirely with to the full diameter. That's why they're using that cord to have decoupled charges. The guys are loading. And then at the end, you can see these no-nail type of detonators connecting from hole to hole according to the fire sequence you want to apply. And then final section, once we were at the bottom of the access shaft, we started going horizontally. We started drifting the tunnels. So basically here, the round, like the length, or let's say the hole depth, or the round depth was 1.8 meter. Again, you could have gone longer in the mining industry, in underground mine. Sometimes it's much longer, but in this case, it's all about the number of explosive per hole being detonated on same delays, because of vibration limits you needed to respect, because you're right next to the mega hospitals with patients in the hospital, people in their surgery and stuff. So vibration limit was extremely important to be followed during these projects. So as Jonathan showed you a cross section earlier of a round, when you're doing tunnels, each hole has their specific sections. So basically here at the bottom, you have your lifters. So that's why according to that legend. Again, that presentation is recorded, so if you're missing some information, you can come back to that presentation. There are a lot of it's quite technical, but basically this is how we started doing. This is how we applied, and we spaced all the holes between each other for the rounds for the excavation of that size. And then in terms of loading, there were two type of holes. So there were the perimeter holes. So it's almost the exact same thing than where we're going vertically. The only difference here is that as we were going deeper and further from the monitoring point, we were able to start loading with more cages of explosive inside the hole. So as you can see here for blast holes, we were allowed, instead of from 2 to 2.5 sticks, we were able to go with up to 4 sticks of Rio Hit 600 series. So by doing so, you're able to blast to take bigger blasts, to have a better fragmentations for the mucking. And then perimeter hole, quite similar. You can see here, instead of half a stick at the bottom of the hole for the perimeter hole, we were allowed to put 1 full stick and still putting the dead cord inside the hole to decouple the charge, to be able to get that well sheared section here of your excavation. And one important detail here is those clay sticks. So usually in underground blasting, because the holes are horizontal, you don't stem the holes because it's too complicated to put crushed stone. But in this case, because noise was an issue and there was a certain noise limit to respect, all the holes were stemmed with clay sticks to make sure there was a confinement, and we're reducing the amount of overpressure generated during the detonation of each of these blast holes. So this is the final result. Of course, once it's blasted, they're gonna finish the inside excavation with concrete. But you still, when you're blasting, you still want to respect the design. You still don't want to be underbreaking the planned excavation. So the concrete excavation at the end, is where it's supposed to be. So that's it for my section. I put my name here, my email with Jonathan's email. If you have any question, you can always. I like to work with LinkedIn. If you have any question, or just like add me to your network of contact. And it's always good to chat with some other people from the industry.
Oh, perfect. Well, thank you for your presentation, Jonathan and Marc-Antoine. That was excellent. I'm looking at the chat here, and there's one question, and so the question is, are the pre-splitting holes around the perimeter blasted first in the sequence?
It actually depends. It depends how the rock breaks, to be honest. You can blast it in advance before the blast holes, but the production holes. Sometimes they're going to do it at the same time, so they call it as a buffer shot. So they're going to start blasting the mass holes, and then within the same shot, they're going to take the pre-split holes. It really depends. It really depends on the rock mass, how you're limited in vibration. So it's hard to say. In this in this specific project, the perimeter holes were blasted with the production holes.
Okay, and so I have a question about the pre-shear holes in your design there. So because your bench is only 1.5 meters high, how far down are you drilling those pre-shear holes? Like, did you drill them to full depth and then stem them up to the height where you want to blast, or are you drilling in 1.5 meter increments and stepping in that perimeter each time?
Yeah. So basically, in this case, as a standard, in this case, it's easier to drill these holes to full depth. So from the surface all the way down to the bottom, and that's why we did. If you'd only drill them 1.5 meter deep, you wouldn't need to probe the holes. But when you're drilling the full excavations, I can't remember by heart how deep they were. But if you're starting from the top all the way to the bottom, you need to look at the deviation, because the holes are so tight or so close to each other. You don't want them to start hitting each other. So that's why we went for borehole deviation instruments. But most of the time, and I did another type of excavation that was much deeper up north in a hydro dam project, and the holes were 200 feet deep, and everything was drilled in advance. So in this case, but they were being blasted by sections. So when you're loading them, you only want to load them 1.5 meter at a time. You need to put a plug inside these holes 1.5 to 2 meter down the hole, and then you load them. And then you bring them and you blast them as you go and as you bench down your shaft.
Excellent, amazing. Okay, with that, I don't see any more questions in the chat, and we're almost at 1 o'clock, so I think we're going to end it there. If anybody on the call still has questions, please send them to tac-ym@telecom.ca. and I can forward them to both Jonathan and Marc-Antoine. So once again, thank you both for your presentation and presenting today. And to everybody on the call, have a great rest of your afternoon.
Thank you very much.